Okay, we're going to combine a few operations today. Okay, so let's take a look at this. I've got these three matrices. When you look at matrices, before you do any operations, what must you be mindful of before you start do anything? The dimensions. You got to know the dimensions to see if it's allowed. So what are the dimensions? This is what, 2 by 2? This is 2 by 2. And this is what? 1 by, excuse me, sorry, I was messing up. It's row by column, sorry. 2 by 1. Trying to do it with things. So here I've got a 2 by 1 times, what is this, a 2 by 2 minus a 2 by 2. So can this be done? How would I do, what do the parentheses tell me? Do that first. So what would B minus C be? Well, I mean, it would be a 2 by 2, right? What is A? 2 by 1. How much time do I want to waste multiplying these two things? None. I'm done with this one. This is undefined. Yep. You can subtract B and C and get a 2 by 2, but you cannot multiply it on the left side by A. Well, B minus C is going to be what? 1 minus 2, 5 minus negative 3, 3 minus 7, negative 2 minus 2. So I'm saying you could go through all of this work. That's B minus C. But I didn't need to go through that because if I try to multiply by A, that's not going to work. Okay? So look at the dimensions up front to see if they will save you some work. Now let's look at the next one, which is B minus C times A. B minus C is going to be a what? 2 by 2. A is a 2 by 1. This can be done, right? And the result will be a what? 2 by 1 matrix. So B minus C, we just did that. B minus C is, what did I say? Negative 1, 8, negative 4, negative 4. So that's B minus C. So B minus C times A is going to be negative 1, 8, negative 4, negative 4 times, and what is A? 2 and 3, like that. Okay. So the answer is going to be a what? 2 by 1 matrix. So I'm going to look at the first row with the first column, the second row with the first column. So that's going to be negative 1 times 2 plus 8 times 3, and then negative 4 times 2 plus negative 4 times 3. So this is what? Negative 2, 24, negative 8, negative 12. Everybody see that, or do they need to go back? So all we did was we subtracted two matrices, B minus C. That was what we did day 1. And then we multiplied two matrices. That's what we did day 2. So this is B minus C times A. Okay. So keeping in mind the dimensions will guide what the answer is going to look like and whether it's defined or not. Yes, sir.
Isn't that a 2 by 2 though?
This one right here. Negative 2. Oh, sorry. Yeah. Gosh, I got to back up. Yeah, that you guys should have looked confused with what I did there. Let me back up. Answers are 2 by 1. Sorry about that. So negative 2 plus 24 is what? 22. And negative 8 plus negative 12, negative 20. That's the answer. 22, negative 20. Sorry about that. Okay. So here I am telling you to pay attention to the dimensions in the arithmetic, and I'm making all of those mistakes for you. So answer is a 2 by 1 matrix. So here we did subtraction and then we multiplied. So there are some properties for matrices. The associative property, and I will not test you on, you know, definitions, left distributed property. I'm not going to test you on this kind of stuff, but this should be pretty basic knowledge when you see it. If I have A times BC, that should be the same as AB times C. It doesn't matter which order you multiply those, okay? So again, I'm really not going to hammer you on spit out these properties for me, but these are just things in working knowledge you should get. The left distributed property. If I have A times B plus C, that's the same as I can add B and C together and multiply by A, or I could just say AB times AC. Okay. The right distributed property, B plus C times A, that's BA plus CA. And the associative property of scalar, if I have a scalar number K times AB, that's the same as K times A times B, or A times KB. It doesn't matter where that scalar number goes, okay? So these are just properties with matrices. Associative means it doesn't matter if I'm multiplying these things left or right, it doesn't matter which two I multiply first. Same thing here, when I distribute, I can distribute from the left or I can distribute from the right. And then if you're multiplying by a number, a scalar, it doesn't matter where that goes, okay? So let's do a couple and just prove this. I've got matrices A, B, and C, and these are typical questions. Well, I'll give you 1, 2, or 3, 4 matrices up top and then ask you several questions about them. Prove that A times B plus C is equal to AB plus AC. So what I want to do in this one, on the left side, let's figure out what A times B plus C is. And on the right side, let's figure out what AB times AC is, and those should equal. Okay, so let's figure out. So I've got A times B plus C. So that's going to be 1, 0, 0, 1. That's A times B plus C. So B plus C is going to be what? 2 plus 1, negative 1 plus 2, negative 1 plus 3, and 2 plus 1. Now, if you don't need to write this extra step, that's fine. So this is 1, 0, 0, 1 times 3, 1, 2, 3. And now I just multiply these out. So it's going to be, what would the size of the answer matrix be? A 2 by 2 matrix. So I'm going to go first row, first column, first row, second column, and then second row, first column, second row, second column. So the first element is going to be 1 times 3 plus 0 times 2. The next element, first row, second column, is going to be 1 times 1 plus 0 times 3. Second row, first column is going to be 0 times 3 plus 1 times 2. Second row, second column, 0 times 1 plus 1 times 3. And this is, that number is 3. What's this one over here? 1, 2, and 3. Am I going too fast? Are you getting the multiplication? And what I did not do, remember on the yesterday when I did this, or Friday, I told you that you're going to have a, 1, 1. If you still have to write this down, that's fine. If you have to write down, these are the elements. This one comes from first row, first column. If you have to do that, that's fine to keep in your head where the multiplication happens. So that's adding B and C and then multiplying by A. Let's do it the other way. The other way says, what is AB plus AC? That's going to be 1, 0, 0, 1. That's A. And then what is B? 2, negative 1, negative 1, 2, plus AC. So are these defined, these multiplications? Yeah, 2 by 2 times a 2 by 2. So see if you can do this. How do I get the first element right here? It's the first row with the what? First column. So that's 1 times 2 plus 0 times negative 1. What number is that? 2. Okay. If I move over here, first row with the second column, that's 1 times negative 1 plus 0 times 2. What number is that? Yeah, negative 1. These zeros make it easy to do the arithmetic. Now if I come to the second row, first column, 0 times 2 plus 1 times negative 1. What number is that? Negative 1. Second row, second column, 0 times negative 1 plus 1 times 2. What is that doing? What is that matrix doing? Yeah, multiplying by a matrix that has 1s in the diagonal, I end up with the same thing I started with. So in number sense, what number do you multiply and keep the number? 1. It's the matrix equivalent of multiplying by 1. So we'll do the next one here. This is going to be 1 times 1 plus 0 times 3. 1 times 2 plus 0 times 1. 1 times, oh, I had a mistake here. That's a 0. And then 0 times 1 plus 1 times 3. 0 times 2 plus 1 times 1. And now I just simply have to add these two together. So if I add these together, 2 plus 1 is 3. Negative 1 plus 2 is 1. Negative 1 plus 3 is 2. 2 plus 1 is 3. And if I did that right, these are the same matrices, okay? So I got the same answer. So again, nothing really new here. It's just that we've got addition and multiplication coming together in the same problem. Now we need to move on to a measure about a matrix. Dimension is the one way we've talked about measuring matrices so far. Dimension tells you the size. We need to talk about something that's a measure of a square matrix. What's a square matrix? Yeah, 2 by 2 is a square matrix, but more general, it has the same number of rows and columns, okay? We can measure something called the determinant of a square matrix. Think of it like, you know, if you're a quarterback, how do they measure quarterbacks in the NFL? What stat? Anybody? Passer rating. You know, so they have a rating for you, so it tells you how good you are. What do you measure to tell how good a student is when they're leaving high school? Your grades, but your GPA. So it's a measure, okay? So the determinant is a measure of a matrix, and we are not going to do this, but when you hit physics, you'll learn that if these matrices represented forces, the determinant tells me where the force sort of averages out. So anyway, that's beyond the scope of the class, but the determinant is a measure of a matrix, okay? Just like if I had a cube, the volume would be a measure of how much space it took. So a determinant is another measure that we have for a matrix. So let's talk about how we find the determinant for a 2 by 2 matrix. You can only find the determinant of a square matrix. You will never be able to find the determinant of a matrix that's not square. So this only works on square matrices. For a 2 by 2 matrix, this is the notation we're going to use. It's either going to be like DET, that means the determinant, or if you see the absolute value signs around a matrix, it doesn't mean absolute value, it means determinant. This is just an example where math, we run out of symbols and we keep using the same thing over and over again. So when you see absolute value, what looks like absolute value signs around a matrix, it means the determinant. So if I've got a 2 by 2 matrix, the determinant is found by multiplying this number and this number. So that's A11 times A22 minus A21 times A12. Okay, so the way I look at it is you look on this diagonal. You multiply these numbers, like multiply A and D minus B and C. Okay, so you look on the, going from the top left to the right, you multiply those numbers and then subtract the numbers that you have going up the other diagonal. So it's a pretty simple algebraic exercise, or arithmetic exercise, but I think you can handle it. So the determinant of B is going to be, how do I find, what numbers will it be? 1 times negative 2 minus what? 3 times 5. So you look at the first, you go down that diagonal and multiply, and then you subtract the other diagonal. So this is negative 2 minus 15, which is what number? Yeah, negative 17. So the determinant of that matrix is negative 17. Okay? Let's do a few others. Well, let me give you another one. I didn't have another example. Let's find to find the determinant of this matrix. You can just write this example in. It's going to be what? 6 times 7 minus 8 times 5. So that's 42 minus 40, which is 2. So that determinant is 2, okay? So that's how we find the determinant of a 2 by 2 matrix. It gets harder with a 3 by 3. We will not make you do a 3 by 3 by hand. That's something we're going to use the calculator for. So the only ones you're going to learn by hand are just the determinants of 2 by 2 matrices. So we talked about this a minute ago in that example we had earlier, but if these are real numbers, 1 times x is equal to x times 1. That's the multiplicative identity. It means when you multiply something by 1, it stays the same. That's the multiplicative identity. With matrices, there is a multiplicative identity for every square matrix. We saw this a moment ago. In a 2 by 2 matrix, this is the identity. You put 1s on the diagonal, 0s everywhere else. That means if I multiply this by any 2 by 2 matrix, what will my answer be? The same. It doesn't change it, okay? So if I start with any 2 by 2 matrix and I multiply it by this, I get the same matrix I started with. Here's my 3 by 3 identity. Here's my 4 by 4, okay? So these are just the matrix equivalent of multiplying by 1. So let's look at an example here of doing this, just so you can see this. If I multiply these matrices, so this is what, 2 by 2? And this is what, 2 by 2? The answer is 2 by 2. So it's going to be 1 times A. So it's first row, first column. 1 times A plus 0 times C. What number is that? It's A. Now let's go over here, first row, second column. What's 1 times B plus 0 times D? That's B. Now let's move to second row, first column. 0 times A plus 1 times C. What is that? C. And then second row, second column, 0 times B plus 1 times D. That's just D, okay? So I got what I started with. Same things happen here. A times 1 plus B times 0. That's A. A times 0 plus B times 1. That's B. C times 1 plus D times 0. C times 0 plus D times 1 is that. So that's what the multiplicative identity does. It's a matrix equivalent of multiplying by 1. So when we have the matrix identity, when we multiply by the multiplicative identity, the matrix doesn't change. Okay, so with real numbers, you know that x times 1 is equal to x. Okay, you can also divide both sides by x, and you get that x over x is equal to 1. Okay, that's pretty straightforward as long as x is not equal to 0. Now, suppose I've got something like this. Here's my multiplicative identity matrix. I've got the identity matrix times A, B, C, D, and that's going to be A, B, C, D. Okay. But I cannot divide by A, B, C. I can't say, let's divide both sides by A, B, C, D, like you did here. You can divide both sides by X, and you get 1 is equal to 1. You cannot divide by matrices. That's the only operation is not there. So what we need to talk about, instead of dividing by a matrix, we need to multiply by what we call the inverse of a matrix. Okay, so let's talk about what an inverse matrix would look like, and we're going to talk a little bit more about this in the lesson we have tomorrow. So since we can't divide by matrices, we need to multiply by the inverse of the matrix in order to accomplish this. So for a square matrix A, so again, square matrices are the only ones that have determinants. Square matrices are the only ones that will have inverses. Not every square matrix will have an inverse, but most of them do, and you'll figure out when and why that doesn't happen. So if a matrix A has an inverse, then A times A inverse, or A inverse times A, it doesn't matter the order here, will give me back the identity matrix. So what matrix can I multiply any given matrix by and get the identity matrix? That is the matrix that has all ones on the diagonal and zeros everywhere else. So I want to show that these two matrices are inverses of each other. So if A and B are inverses, I should be able to multiply A and B, and what should I get as my answer? I should get, this should be my answer. I should get the, if these are inverses, when I multiply them, I'll get the identity. So let's look at what AB is. So that's going to be 9, 5, 7, 4 times 4, negative 5, negative 7, 9. Okay, so can this be done? Yeah, 2 by 2 times a 2 by 2. So I'm going to get the first element is going to be 9 times 4 plus 5 times negative 7. Okay. Now the first row with the second column is going to be 9 times negative 5 plus 5 times 9. Now the second row with the first column is going to be 7 times 4 plus 4 times negative 7. Second row, second column is 7 times negative 5 plus 4 times 9. So what, this is what, 36 minus 35, which is what? 1. This is negative 45 plus 45. This is 28 minus 28. And this is 36 minus 35. So these two matrices are inverses because when I multiply them, I get the identity back. Okay. This is similar to like when you have 2, what do you have to multiply 2 by to get a 1? 1/2. So in real numbers, 2 and 1/2, they're multiplicative inverse of each other. You multiply 2 by 1/2 and you get 1. But with matrices, what matrix? These two matrices are inverses. Now to prove it fully, I have to prove it both ways. I have to show that BA, so that's 4, negative 5, negative 7, 9 times 9, 5, 7, 4. I have to show that this is also equal to the identity matrix. So if I multiply this, I get what? 36 minus 35, which is 1. And then I get what? 20 minus 20 is 0. The second row, first column, negative 63 plus 63 is 0. Second row, second column, negative 35 plus 36 is 1. So those two matrices are inverses of each other. Questions over that? Now, what we got to figure out is how do we determine an inverse? Because that's going to help us solve some of the problems. So we have a formula for 2 by 2 matrices. If you have a 2 by 2 matrix, okay, we know the determinant is going to be AD minus BC. The inverse of a 2 by 2 matrix is 1 over the determinant times, there's a special name for this matrix called the adjugate matrix or the adjoint matrix. How do I get from this matrix to this matrix? What happened? Somebody tell me. Two things happen. Come on, guys. I'm here and I ended up here. What happened? This would be the interactive portion of the class. So it's all A, B, C's, and D's, right? But what happened? What happened with A and D? They switched places. What happened to B and C? I stuck negative signs in front of them. That's all that happens here, okay? So to find the inverse of a matrix, it's 1 over the determinant. On this diagonal, you switch A and D. Okay? On this diagonal, whatever the signs are, you change them. Okay? And that gives you the inverse. Now, can you think of when the inverse will not exist? There's an operation there that might give me something not being defined. What is that? Okay, not a square. I can't find. That's one point. I can't find the inverse. But look at this right here. I'm going to give you a clue. Look at this part of the formula. When am I going to run into trouble? Yeah. If the determinant is 0, I will be dividing by 0. When can you divide by 0? Answer is never. Okay. So when would the matrix not exist? So it does not exist when the determinant, and I'm just going to abbreviate that, is 0. Okay, because I cannot have a formula that says 1 over 0. Okay, so if the determinant is 0, then there will be no inverse of this matrix. So let's find a few examples of finding an inverse. The first step to finding the inverse is to find the determinant. So the determinant of this matrix A, how do I do that? It's 4 times 10 minus what? 2 times 19. That's 40 minus 38, which is 2. Okay, the determinant is equal to 2. And then to find the inverse, we have a formula. You're going to need to know this formula. The inverse is 1 over the determinant times the adjugate matrix. So here the inverse is going to be 1/2, and then the adjugate matrix. What do I do? The adjugate matrix does what? Does two things. How do I get from here to this adjugate matrix? We talked about it. Yeah, so on this first diagonal, what happens? They switch places. On the other diagonal, what happens? Yeah, I just change the signs. And that's it. That is the inverse matrix. Okay? So we want to go one step further. Let's multiply this 1/2. And we get our final answer. What is 1/2 times 10? 5. And then I'm going to have negative 19 halves. Leave it as a fraction. What's negative 2 over 2? Negative 1. And what's 4 over 2? That's 2. Okay. So this is the inverse of my original matrix. Okay. I wonder if I make you prove it next. We can do that. So I've got two matrices. I found the inverse. How can I prove that I found the inverse? Multiply them and I get what? Ones on the diagonal, right? And zeros everywhere else. So let's prove one of these. I'm not going to prove both of them. So A, what was matrix A? What was it? 410? 410, 219? Was that it? That was A. Okay. And then we found the inverse. I'm going to leave it like this. That's what we said the inverse was, right? Is that what we found a minute ago? Okay. So I'm going to multiply A times A inverse, and I should get the identity. So let's try that. So 4, 19, 210 times 1/2 times 10, negative 19, negative 2, 4. Now the reason I kept this 1/2 out is like, I just want to hold it out to the end, because if I put this 1/2 in this matrix, I've got fractions. So let me try to hold off. So I'm going to pull this 1/2 in front. So it's 1/2, 4, 2, 19, 10, 10, negative 19, negative 2, 4. Okay? And now I just need to multiply these two matrices and then take 1/2 of it. So if I do this operation, looking at the first row, so first row, first column, that's 4 times 10 minus 2 times 19. What's 4 times 10? 40. 2 times 19. 2 times 19 is 38. 40 minus 38 is 2. Okay. Now let's look at first row, second column. 4 times negative 19 plus 4 times 19. I don't know what 4 times 19, but I know that 4 times negative 19 plus 4 times 19 is 0. Okay. And then I move here. What's 2 times 10 minus 2 times 10? That's 0. And then second row, second column. 2 times negative 19, negative 38 plus 40 is 2. And then what happens when I distribute that 1/2 in there? Yeah, I get the identity matrix. Okay. And we're there. Now, you could switch these matrices around the order and prove that A inverse times A. I'm not going to do that. I'll just leave that for you. But anytime, you've got a formula now for finding the inverse. First step to finding the inverse is finding the what? Determinant, and then 1 over the determinant times the adjugate matrix. So you can always check your answer. I'm not going to make you check your answer every time. So let's find the inverse here. So to find the inverse, first step is to find the what? Determinant. So the determinant of A is what? 6 times 4 minus 8 times 3, which is what? That's 0, right? Yeah. So here, when the determinant is 0, the inverse is undefined. So because the determinant is 0, the inverse is undefined. Because remember, the inverse is going to be 1 over the determinant, okay? So you cannot divide by 0. So the minute you get a determinant of 0, the inverse of that matrix is undefined. So less work to do once you get there. So let's just make sure we're good on finding inverse. First step is to find what? Determinant. The determinant of this matrix is what? 21 minus what? 2 times negative 1? Is that right? So that's 21 plus 2, which is what? 23. Okay. So it's 21 minus negative 2, that's 23. So the inverse is what? 1 over what? 23. And then the adjugate matrix. Not arithmetic here, it's just switching things. So what switches places? 7 and 3 switch places. And then I get a negative 2 and a positive 1. And that's it. Okay. So that is the inverse matrix here. Now, final step is just distribute that 23 inside. So your answer is what? 7 over 23, 1 over 23, negative 2 over 23, and 3 over 23. So it's ugly, it has fractions, but you really didn't have to work with them. You hold them out to the end. Yeah, if you can do it, but if somebody had something like, if you wrote 4 over 6, I'm not going to count off that you didn't write 2/3. I'm a little bit lenient on that. You got the right spot. Yeah. So, you want to be in the habit of reducing as much as you can, but you've done the heavy lifting, so you should be good. Somebody tell me, okay, what's the determinant here? Yeah, it's going to be, it's negative 1 times 1 minus 0. That's negative 1. So the inverse is going to be what? 1 over negative 1, and then how do I switch to get the adjoint matrix? What switches places? Yeah, so the 1 and the negative 1 switch places. I put negatives in front of the 0, but do I really need to do that? No, that doesn't really change anything. So I've got a negative 1 times all of this. What's the final answer? Okay, it's going to be what? Negative 1, 0, 0, 1. What does that mean? This matrix and its inverse are what? The same, okay? So this matrix and its inverse are the same. When I multiply those two matrices, what should I get? You multiply a matrix and its inverse, what do you get back? All ones on the diagonal, zeros everywhere else, okay? And I think this is toward the end. Is this the last one? So what's the determinant of this one? It's 1 times 1 minus 0, which is 1. So the inverse is 1 over 1. And then what's the adjugant matrix here? What switches places? How can you tell? It doesn't matter. And then I do what? I put negatives there. What is this? This one you expected. This is, what matrix is this? This is the what? This is the identity matrix, okay? This is saying when you multiply the identity matrix, its inverse is the identity matrix. So that means, it's like saying 1 times 1 equal 1, okay? So in this case, the inverse of the identity is the identity, because when you multiply the identity times the identity, you get that identity back, okay?